Hey guys, today we're going to talk about atoms. And the interesting thing about atoms is that they're too small for us to see. There's no microscope in the world that will allow us to actually look at an atom. And so we use conceptual models to describe these. But atoms are still there, and they're made up of three basic subatomic particles. You see a chart over here that highlights those for you. Proton, neutron, and electron. You'll notice that the proton has a positive sign in it. And that's because protons are positively charged. They are found in the nucleus of an atom, along with these purple balls that represent neutrons. You'll notice that electrons have a negative charge. They have that negative sign there. They're found out here in this electron cloud, and they're negatively charged. This particular model shows that there are 2 electrons in this particular line and 4 out here. It's a different model where it's showing you the different orbitals of those electrons. They get pretty complicated, but for us, I need you to understand that electrons are found out here in the electron cloud. If we talk about those charges, they're very important to the properties of an atom. First and foremost, opposite charges attract. So if I have a proton and an electron, they will want to be near each other. They'll balance out. Like charges repel, so 2 protons will repel and 2 electrons will repel. And since like charges repel each other, that might bring up the question of how a nucleus stays together. Because remember, all of the protons are kept in the nucleus. Well, the answer to that are these neutrons. Those neutrons help hold together those protons. If you look here, this is a carbon-12 nucleus. It's got 6 protons and then 6 neutrons. The protons and neutrons are not always the same number, but with this particular atom they are. Those neutrons and protons are found in the center of an atom. And what we need to understand about these regions of the atoms is that they're very important properties that make up how atoms behave. Most of the mass for an atom is found in the actual nucleus, or that center region. Protons and neutrons are said to have mass where we say electrons don't. If we made a neutron have a mass of 1, relatively to it, a proton would be very close to 1, see 0.9986, etc. It would round all the way up to this 4th place out here. Electrons, on the other hand, they have such a small mass that we'll just ignore their mass altogether. So in general, you have this small, massive nucleus and then a rather large, but mostly empty negative electron cloud. If we talk about atoms, there are different types. A chemical element is a pure substance that consists entirely of one type of atom. If we look over here, this element we're looking at is mercury. It's a metal that is actually liquid at room temperature. There are more than 100 elements known, but most of them are not commonly found in nature. There's only a couple dozen that are found in nature. And of course, they are represented with letters. And so we're going to use these letter combinations to represent them. It's single letters, and they're always capital, unless we have a double letter. And then you'll notice that the first letter is capital, and the second letter is lowercase, like Na for sodium, or Hg for mercury, which we're taking a look at here. This is the periodic table of the elements. It's much more than a list, and it gives you a ton of information about each one of these elements. We have another video that'll come up that'll talk about that, but in general, you can find all the elements on here. For instance, if we go ahead and find aluminum, which is the type of foil you might have in your house, you'll notice that it's right here on the periodic table. Its atomic number is 13. That tells you that it has 13 protons, 13 electrons, unless it's an ion, and then the average atomic weight is 26.98. And what that means is that if you took all of the aluminum isotopes in the world, you would then have an average mass of 26.98. What is an isotope? Well, an isotope is an atom that has either gained or lost electrons. You'll notice once again I have my carbon-12 atom over here. I have 6 protons, 6 neutrons, and those 2 things added together give you a mass of 12. But there's also carbon-13 and carbon-14. Well, you can't change the number of protons because the number of protons determines which atom you're talking about. If we flip back for a moment, you can see that carbon has 6 protons. If we added a proton to it, it would become nitrogen. If we subtracted a proton from carbon, it would become boron. So we can't add or subtract protons, so if we're going to increase the mass and make carbon-12, carbon-13, or 14, we have to add neutrons. Isotopes are atoms of elements that have gained or lost neutrons. Some of these isotopes are radioactive. So if we look here at carbon, Non-radioactive carbon-12, non-radioactive carbon-13 are very common, but radioactive carbon-14 is uncommon. If you notice, the number of neutrons changes. The electrons don't change, the protons don't change, just the neutrons change in an isotope. We find isotopes of almost every single element in the world, and sometimes they're very important for us. For instance, we can radiometrically date something using carbon-14 if it's within the last few thousand years. If we go farther than that, we could use the decay of argon into potassium. That particular decay is much longer, and we'll use it to date some of the oldest rocks on Earth. That leads us into compounds of these elements because they don't stand alone. In fact, very rarely in nature do you find one element pure in nature. Most of the time they're compounded with other things, or they're put together. The physical and chemical properties do change when we have those compounds. For instance, we have hydrogen and oxygen. Hydrogen is extremely flammable and it's a gas, and oxygen is used in almost every flame or every burning reaction, and it's also a gas, and it's useful for us in our cellular respiration. These are the reactants of this reaction. That means they go in, and so what ends up happening is these reactants will produce a product. If we take hydrogen, we set it on fire, it reacts with oxygen, and then it forms water. Of course, the water it will form right after that reaction is vapor water, but eventually it will look like this water. Liquid water. Completely different properties than both hydrogen and oxygen. Again, reactants go in, and water, which is our product, comes out. So let's take a look at that reaction in full. If we take a look at this video one more time, I kind of narrate for you. Of course, there's flame here, and that flame has some energy to it, and it's gonna give enough energy to get over the activation barrier of this hydrogen gas, which is trapped in a balloon. When we start the video, you'll see the flame is moving closer to. As soon as it breaks it, immediately you have a huge reaction. The slow motion version shows you the big ball of flame, and if you see that distortion in the air, that's your water vapor. Hot water vapor, and of course it's generated by hydrogen reacting with oxygen in the air. If there was no oxygen, the hydrogen would not have burned. If there was no hydrogen, then the oxygen would not get used in the reaction. Either way, this process formed water. There are two main types of chemical bonds: covalent and ionic bonds. Covalent bonds actually share electrons. So if you look at this particular diagram, you can see the two electrons right here are being shared between hydrogen and oxygen. Hydrogen has one electron. Oxygen needs two more electrons in its valence shell, which is the shell on the outside. And so what it does is it shares one electron with hydrogen and another electron with a different hydrogen to fill that outer shell. Oxygen's outer shell wants 8, and if we take a look here, we have 1, 2, 3, 4, 5, 6, 7, 8 in there now because it's sharing with hydrogen. But of course, oxygen has what we call a high electronegativity. And what that electronegativity word means is that the oxygen really, really wants electrons. And so you can tell by looking at this particular graphic that the electrons are going to spend more time near oxygen than they are hydrogen. And so the hydrogens end up being slightly positive, and the oxygen ends up being slightly negative. That'll play an important role later when we talk about hydrogen bonding. Ions are a little bit different. They're actually going to take electrons. So if we look at this particular graphic, sodium has a full valence shell. 2, 4, 6, 8. It's completely happy. But if you know sodium's atomic number, sodium's actual atomic number is 11. So if it's normal sodium, it should have 11 electrons. But if we take a look, it has 8 on the outside, and then 9, 10, which means this sodium is actually missing an electron. That electron traveled to chlorine. You can see the blue electron here. Notice that the chlorine has a full valence shell, 2, 4, 6, and 8. Which means that we had a swapping or giving and taking of electrons. Sodium was very willing to give up an electron, and it gave it up to a high electronegative atom such as chlorine. What this does is cause a complete charge differential, where sodium is positively charged and chlorine is negatively charged. Think back to our charge rules. Opposite charges should do what? Attract. And so these two things will stick together like a magnet. Now, that sticking together is fairly strong. But ionic bonds are not as strong as covalent bonds. I really like the analogy of using two magnets to represent ionic bonds. They'll stick together, but if you pull hard enough, they'll break apart. And using clasping hands as chemical bonds that are covalent. That clasp hand has so much more strength to it because you're sharing those electrons that this bond is much less likely to break. So the two types of chemical bonds, covalent bonds, are much more strong than ionic bonds. So what does that look like for an ionic bond with sodium and chlorine? Well, that forms our normal table salt, but again, here's that extra electron that's going to move over. And what you end up with is the chlorine having 18 electrons when it's only supposed to have 17, and the sodium having 10 electrons when it's supposed to have 11. And that brings us up to a very, very important distinction to notice about ions, because these are ions, or atoms that have gained or lost electrons. The sodium ion is sodium plus, and the chlorine ion is chlorine negative. What you have to understand is that for every plus sign that an actual atom has, it has lost an electron. So if it's an atom that's plus 4, it lost 4 electrons. If it's an atom that's plus 2, like calcium plus 2, then it's lost 2 electrons. So for every plus sign, you've lost an electron. For every negative sign, you've gained an electron. So this one here is chlorine negative, which means it gained 1 electron. We can see that at the bottom. If it was an atom that was 3 negative, then it gained 3 electrons. These ions that happen in ionic bonding are very important to many biological systems. So now let's talk about van der Waals forces, or van der Waal interactions. These interactions are where atoms will interact with each other with partial positive and partial negative regions. What we have here is diatomic hydrogen. It's called diatomic because the prefix di means 2 and atomic means atom, so 2 atoms. And if you notice, this hydrogen is bonded to that hydrogen, thus 2 atoms of hydrogen bonded together. What we end up with is these slightly positive regions and these slightly negative regions, just like we did with hydrogens in water. And so the attractive force between opposite charges will cause van der Waal interactions to happen. These play a very important role in geckos being able to climb up walls. You see, if we look at the gecko itself, its hands don't look too that special. If we zoom in, we can see that the hands have these little pleats in them, and that increases the surface area. If we zoom in even more, we can see that those pleats are almost like hair-like structures that even on top of them have little pleats on them. What all of this does is create surface area, and that increased surface area allows for more van der Waal interactions. You see, van der Waal interactions are very, very weak, which means that if you only had one of them, it would break easily. But the more you have, the more attraction you have. Think about it like hanging a poster. If you had one thumbtack and a very heavy poster, it probably won't be able to hold it. But if you put 100 thumbtacks in it, now you have 100 times the strength, and that poster is going to stay up. Some scientists work on this in a project called Sticky Boot, where you have an animatronic gecko here, and of course the gecko has man-made representations of what a normal gecko has. And this gecko can climb up and down walls. They don't have the control of a gecko because their robot can't feel, but the principle is van der Waal interactions. You have these many little strengths adding together.